Hello, my name is Alex Fester, and this is my glider project video report. My glider is named Otto 1 after Otto Lilienthal, an early glider pioneer. The objective of the glider project was to design, construct, test, and compete with the miniature glider in a glider fly-off. The project was a capstone challenge for AE 1601 that involved each step of the engineering process from research to prototyping and applied theory learned throughout the course, like weight and balance and aerodynamics. The final deliverables were a video of a glider flight exceeding 20 feet and a video report of the design process. Construction requirements included that the glider could be no larger than 16 inches in length or span, had to be hand thrown, and had to remain intact in flight, and should be built primarily from the provided balsa wood. To measure success against these requirements, I ensured the dimensional and component mandates were complied with, and that the glider did not disassemble in flight. The performance requirements were that the glider had to fly at least 20 feet forward, thrown from ground level, and ideally the glider flew straight with minimal yaw, bank, or pitch movements. I compared the glider's range with the minimum distance and observed its stability characteristics and avoidance of turning in stalls to judge the glider's success. Initial design process. The first design alternative I considered was the tail configuration, critical because the stabilizers provide yaw and pitch stability. The benefits of alternative 1, the T-tail, were that the surfaces are displaced from the airflow around the fuselage and wing, making it aerodynamically efficient. Its two-piece construction also makes it easy to manufacture and reinforce. The main drawback is that the tail was prone and could break in a hard landing. The conventional tail provided an even more simple and secure construction, however, it would not benefit from the T-tail's aerodynamics. Finally, the V-tail could reduce drag by eliminating an entire protrusion, but its construction would be extremely complex and potentially weak. Understandably, I selected the T-tail configuration for its aerodynamic advantages and relatively uncomplicated design. Next, I considered wing dihedral, which determines lateral stability. Positive dihedral will promote stability, minimizing the glider's banking and providing straighter flight. A drawback is that fabrication is more complex with angled wings, and lift is slightly reduced, which could shorten flights. Negative dihedral or anhedral would improve glider maneuverability, potentially allowing special throwing techniques. However, stability would be reduced, so the glider would have a greater tendency to bank. No wing angling would provide for the easiest assembly and no impact on lift. However, the glider would benefit from neither improved stability or maneuverability. I chose to implement dihedral to promote straight flight, a performance requirement, and because the additional design complexity was manageable. Finally, I analyzed wing planform alternatives. A rectangular planform is the simplest geometry and easily reproducible, but the long wingtips would create stronger wingtip vortices and induce drag. In contrast, the elliptical planform minimizes wingtip length and thus induced drag, increasing range. However, the wing area is relatively small at high aspect ratios, degrading lift and distance. The tapered planform is a compromise with medium wingtip length and medium area at high aspect ratios, but no definitive advantage across either metric. I selected the tapered planform as a safe, moderate alternative. It is also fairly conservative in construction complexity. The glider sizing was based on maximizing the wingspan for increased lift. The wingspan was just 1/2 inch less than the maximum dimension of 16 inches. A relatively high aspect ratio was used to minimize wingtip length and induce drag, with the wings tapering from 1.5 to 1 inches. Finally, the fuselage and stabilizer proportions approximated those of manned sailplanes based on reference drawings. For instance, the fuselage length was half the wingspan. The dimension drawing pictures the initial concept. In summary, it features a T-tail, positive wing dihedral, and a tapering planform with high aspect ratio. Testing and design revision. Prototype glider and stability evaluation. The glider center of mass was evaluated using SolidWorks and found to be aft of the wing. Therefore, I anticipated an upwards pitching moment and longitudinal instability. To verify the glider's characteristics, I built a prototype out of cardboard and a pencil. The prototype confirmed the expected violent upwards pitching moment as it immediately stalled and achieved terrible range. To adjust the center of mass, I attached Play-Doh in various positions. The balance testing demonstrated that a large mass was needed on the glider's nose to advance its CG. Balance testing produced the first design iteration, the addition of a canard to securely fasten ballast onto. I also learned that increasing the length of the forward fuselage would advance the CG without additional ballast. Finally, I decided to replace the Play-Doh with more aerodynamic coins. The improved prototype flew distances of 41, 60, and 55 feet, so I felt ready to build my balsa glider. The balsa glider included the planned canard and longer frontal fuselage and was balanced with two quarters. Initial tests of the balsa glider showed decent ranges of 45, 47, and 53 feet. However, the glider had a tendency to bank left or right and was affected by breezes. So, I implemented another design iteration, increasing the dihedral angle from 2 to 6 degrees to improve lateral stability. With the increased dihedral, the glider flew very straight with minimal turning tendencies, even in breezes, as shown in the best test flight video. The glider is seen on the right and is also depicted fitting within the prescribed dimensions. In summary, the design iterations included the canard, longer frontal fuselage, quarters for ballast, and most importantly, increased dihedral. The final glider CG is just forward of the wing's leading edge and about half an inch forward of the quarter chord. The weighted canard ensures a forward CG and nose-down lift moment so the descent is stabilized and the glider does not stall. To estimate the coefficient of lift, I began with the coefficient of lift equation. I measured my glider and conducted additional test flights to quantify the specified variables. The calculated coefficient of lift was 0.157. Similarly, to calculate the coefficient of drag, I calculated the coefficient of induced drag and doubled the result according to the shown equations. I also measured the glider's wingspan to determine the aspect ratio. The calculated coefficient of drag was 1.41 times 10 to the negative fifth. This video shows the best test flight. The distance flown was 71 feet 7 inches and the flight was stable and straight. Revisiting the requirements, the glider clearly met the dimension constraints and remained intact in flight. It far outperformed the minimum required distance and demonstrated stable, straight, and fairly level flight. In conclusion, the glider project was the perfect hands-on culmination of theory from AE 1601. Application is the essence of engineering, and it was rewarding to use my learning to create a product. Now, I'm excited to expand to larger projects later in my AE career. At the glider fly-off, I noticed many students sanded and tapered their fuselages to reduce drag. Going back, I would implement a similar modification to make my design more effective and accurate to manned gliders. Here are my references.